Okay. Well, it's my pleasure to introduce the next plenary speaker, Marcelo Viana, the director of IMPA, the prestigious Mathematical School of Rio de Janeiro, and the former president of the Brazilian Mathematical Society. Marcelo is a Portuguese-Brazilian mathematician with key contributions in the fields of dynamical systems and ergodic theory, and also the recipient of many prizes and awards, which I will not list here. He's also a gifted speaker and a born communicator. So without further ado, let me give him the floor. Please, Marcelo.
Thank you very much, Pedro. Thank you all for being here, and especially thank you to the Portuguese Math Society for this invitation. I'm glad to be here. I would be even more glad if I were in person in Porto. I sincerely hope this will be my last online lecture in a very long time, and that next time we'll meet in person wherever that may be. So I will be talking about three notions and the interconnections between these three notions. They will appear gradually during the presentation. One of them is absolute continuity, then Lyapunov exponents, and then rigidity, which has in dynamics has a very precise meaning, and the connections some connections between these notions I hope to make clear in the presentation. The presentation itself is based essentially on a series of joint works, mostly with Artur Avila from IMPA and Zuich, Amie Wilkinson from Chicago, and Jagan Yang, who's a professor at Federal University Fluminense in Niterói, near Rio. And more precisely based on three papers that we published along the years. The latest one is to appear in the volume of Ergodic Theory and Dynamical Systems in memory of Anatolika talk, probably this year. So let me start with the kind of object that we want to study, and those are diffeomorphisms on compact manifolds. And we consider this class of diffeomorphisms called partially hyperbolic. That means that at every point of the tangent space to the manifold, one has a decomposition of the tangent space into three directions, into three subspaces. This decomposition is assumed to be continuous, meaning that if you take X and X prime, which are closed, then the corresponding EU, EC, and ES will be closed in some arbitrarily chosen local chart for the tangent bundle. And so let me try to draw a picture here. We have this decomposition into three directions, and at the point X. And this decomposition is assumed to be invariant, meaning that if you look at the decomposition at the image point, f of x, at f of x, then the derivative of your map takes the decomposition from the point x to the point f of x in such a way that each subspace is mapped to the corresponding subspace at the point f of x, at the image point. So that's what's written here. That's what this means. The EU of x is mapped by the derivative onto the EU of f of x, and the same thing for EC and ES. U stands for unstable, so we call EU the unstable subspace at the point x. C stands for center, and S for stable. And the reason for this denomination is the second half of the definition of partially hyperbolic. We want the derivative along these subspaces to have rather specific behavior. Along the stable subspace, the derivative should be uniformly contracting, which means that for some choice of the Riemannian metric on the manifold, so M is assumed to be a Riemannian manifold, we are allowed to change the Riemannian metric within the same equivalence class of Riemannian metrics in such a way as to have that the norm of the derivative along the stable subspace should be uniformly bounded above by a constant smaller than 1. That's what I mean by uniformly contracting. The behavior of the derivative along EU, along the unstable subspace, is dual, meaning it's assumed to be uniformly expanding, which just means that the norm of the inverse of the map is uniformly bounded from 1 in the way I described. And the center direction, well, it's called center because it's assumed that the behavior of the derivative along EC is somewhere in between those two behaviors that I described previously. So if you take a vector VC along this subspace and you compute how much the derivative dilates this vector under iteration, so if you calculate this quotient, then it should be, this dilation should be strictly smaller than whatever dilation you have along the unstable space by a factor, and by a factor smaller than 1. And similarly, or dually, this dilation along the center should be strictly larger than whatever expansion or contraction you have along the stable subspace. So VC stands for any vector in EC, VS for any vector in ES, and VU for any vector in EU. So we have very definitely contracting directions in your tangent space, definitely expanding directions in your tangent space, and then possibly some directions where the behavior is somewhere in between, but in between also means that there is a definite factor separating the two, separating it from the other two behaviors. And an important thing to keep in mind, it's basic, it's not difficult to prove, not trivial either, is that partial hyperbolicity is a C1 open property. What this means is that if you have a diffeomorphism which satisfies the conditions that I described for some choice of lambda, then possibly up to increasing lambda slightly, but still smaller than 1, any diffeomorphism which is C1 close to the initial one will still have this property, okay? So in the space of all diffeomorphisms with the C1 topology, the subspace of those which are partially hyperbolic, which satisfy this condition for some lambda, is an open subset. And that's useful to keep in mind because it means that whenever I exhibit an example of the partially hyperbolic diffeomorphism, I am in fact exhibiting a whole class of examples. It's never too specific, too particular. The C1 topology just means that two diffeomorphisms are C1 closed if they are uniformly closed and their derivatives are also uniformly closed. That's what C1 topology means. So this is the class of dynamical systems that one wants to study. And I should make an observation here that I kind of implicitly, I think I gave you the impression that I'm asking ES, EU, and EC to be non-trivial, but in fact we may be flexible about that. We may in some cases assume that one of them, any one of them, reduces to the zero, to the trivial vector subspace. And there's one particular example where, which is historically important, and that's one special case. And that's a special case where the center subbundle, where there's no center, where the center subbundle reduces to the zero vector. And in that case, that's an older notion, which goes back to the 1960s. And we say that F is just hyperbolic. It has just the expanding and the contracting directions, and that's hyperbolic. Sometimes we add the word uniformly just to stress the fact that lambda is the same for every point. That's what the uniformity means. And and also sometimes it's such systems are called anosive systems. They were introduced in the 1960s by Stephen Smale, and in his efforts to find a class of dynamical systems which would be general in some sense, which would contain most dynamical systems, and which could be understood. The understood part was fulfilled. We understand the uniformly hyperbolic systems very well, not completely, but rather well. But the hope that they would be almost all dynamical systems, that one turned out to be misguided, and that's the reason why we want to look for more broader classes of dynamical systems. But uniformly hyperbolic systems were used almost immediately by Anosov and Sinai for one important and specific goal, which was to extend the theorem of Hedlund and Hopf about the geodesic flow on surfaces of negative curvature. So let me just draw a picture to try to explain what is the geodesic flow. You have a manifold, and on the manifold you consider a geodesic. So this is a Riemannian manifold. You consider a geodesic, you consider a geodesic on the manifold, say parametrized by arc length, which means that the tangent vectors are dimension are the norm 1. So this is the derivative of the geodesic at the point x. Then you look at the point gamma t of x, gamma being the geodesic, and you consider the tangent at gamma t. So you have here a map which sends the initial vector, the initial tangent vector, to another vector, which depends on the time you let pass and on the initial vector. And this phi sub t is the geodesic flow. So the geodesic flow is formally a map, a family of maps on the unit tangent bundle to the manifold, which just takes one vector, considers the geodesic, one unit vector, considers the geodesic tangent to that vector, lets the geodesic evolve during time t, and looks at the new tangent vector. And that's the geodesic flow. And Hopf and Hedlund had proven that if the manifold is a surface with negative curvature, then this dynamical system is ergodic. Ergodic in the sense that if you take time averages, these are volume-preserving dynamical systems, and if you take time averages along trajectories, what you get as the average is precisely the space average of your function with respect to the to the natural volume measure. So what Anosov used the notion of uniform hyperbolicity for was to prove this theorem that, in fact, the geodesic flow of any compact manifold with negative curvature is ergodic. So the Hedlund-Hopf theorem holds in any dimension. That involves some very serious difficulties. And in a nutshell, the way uniform hyperbolicity enters this picture is because Anosov proved that if the curvature of the manifold is negative, then its geodesic flow is uniformly hyperbolic, belongs to this class of dynamical systems that we are describing. And together with Sinai, they proved that volume-preserving flows which are uniformly hyperbolic are ergodic. So you put these two things together, and you get the fantastic theorem of Anosov, published in 1967, announced in 1962, and published in 1967. So this was this one example, one particularly striking success of the theory of uniform hyperbolicity. But by the late 60s, early 70s, it was clear that that there are many systems which are not, in fact, hyperbolic, And there was a flux of proposals of broader and broader notions of trying to give definitions which would be have a broader scope than uniform hyperbolicity in an attempt to catch up, to recover that dream. And most of those notions simply disappeared, died out. But partial hyperbolicity remains, and this has been a major topic in dynamics over the last 25 plus years. It was, the study of partial hyperbolicity was started by Breen and Piesin in 1974. They raised in particular the issue of ergodicity. I mean, having proved that uniformly hyperbolic dynamical systems are ergodic, have this average, time average equals space average property. What can we say about the larger class of partially hyperbolic systems? That was already in their paper. And at about the same time, Hirsch, Pugh, and Shu were developing the theory of normal hyperbolicity, which is very much related to these topics. Before I proceed, I want to give you a few examples of constructions that yield partially hyperbolic diffeomorphism, because I hope this will help you focus and make the discussion more concrete. And also because I will be talking about this kind of examples later on. So one way to construct a partially hyperbolic map is to take a matrix with integer coefficients, and whose spectrum has eigenvalues whose norm is both smaller, equal, and greater than 1. And then you just look at the map. This induces on the torus. And the fact that the matrix has integer coefficients means that there is a map induced on the torus. And since the determinant is 1, this map will be a diffeomorphism of the torus, and it will be partially hyperbolic. The stable, unstable, and center direction coming from the eigenvalue, the eigenspaces associated to the 3 types of eigenvalues. Another important construction is that you start with a flow, a hyperbolic flow, uniformly hyperbolic flow. This, by definition, means that the tangent space can be split into an unstable direction, a stable direction, and also the direction of the flow. And instead of looking at the flow, we just take the time one map, and that's the diffeomorphism, and it's partially hyperbolic with a partially hyperbolic decomposition that corresponds to the the one given by the flow. The interesting thing is that once you take the time one map, you are allowed to perturb it, to change it as a diffeomorphism. And most perturbations, most changes of a time one map of a flow are not time one maps of a flow. So you get into a much larger setup here. And finally, my third classical construction of partial hyperbolicity is to start with something which is hyperbolic and then just multiply by something which is very neutral. Now, we call in particular this construction rotation extensions. You just, on the second variable, you take the dynamics to be a translation. On the first variable, you have hyperbolicity, you have an Nosov. On the second, you just have a translation, and that is, again, partially hyperbolic. The center direction in this case corresponds just to the vertical, to the direction of the fibers. Now, the one reason why partially hyperbolic systems are a good topic of study is that they have nice geometric properties. And the main one, whose proof is contained in those papers, is that the stable and unstable subbundles are uniquely integrable. There exist unique foliations which are tangent to these bundles at every point. And if you still recall your differential topology course, this may make you think of the Frobenius theorem for integrability of distributions. But in fact, this is a different matter because these bundles in general are continuous, not differentiable. So the Frobenius theorem doesn't really play a role here. These are just continuous objects. The fact that despite the lack of regularity, these bundles are integrable is really a dynamical thing. It's because they have dynamical properties, namely the fact that the derivative is uniformly contracting or uniformly expanding. Since the bundles themselves are not differentiable, you should not expect the foliations to be differentiable. You should not expect them to have a lot of regularity, and that's basically the main result in Laws of Sinai, 1967, these foliations are absolutely continuous. The projection, if you take two cross sections to the foliation as in the picture, and you look at the map that is given by the projection along the leaves, this map here, which is called the allonomy map, then these maps, they are not necessarily smooth, but they preserve sets with measure 0. By the way, this is the main difference between Hopf-Edlund theorem for surfaces, where the allonomies that appear, the foliations that appear, turn out to be C1, and the general theorem of Anosov in higher dimensions, where in general these foliations are not differentiable, but still they are absolutely continuous, and that's what makes that's the key argument that makes the theorem work. However, and that's where getting into partial hyperbolicity makes things become more interesting. However, the center subbundle is a much more subtle object. It may not be integrable. When it is integrable, it may not be uniquely integrable. There may be more than one foliation tangent to this center subbundle. And even when the foliation exists and is unique, it needs not be absolutely continuous. So here we have a lot more opportunity for experiencing the differences, the new difficulties and the new interesting questions that are raised by going from uniformly hyperbolic to actually partially hyperbolic. And here is a construction, an explicit example that is already more than 20 years old. It's a rotation extension of a particular type. On the first variable, you consider just this linear automorphism of the torus. And on the second variable, you consider the identity, rotation by 0. And then it is known out of general facts that if you take such a map, a very simple model, and you perturb it, any perturbation is, well, partially hyperbolic because that's an open property. It has a unique center foliation, and moreover, topologically, we know what the foliation is. For F0, the center foliation, for F0, it's just the foliation by vertical circles for F0. And for F, for a perturbation, it will be essentially the same, except that the circles are smooth, but not straight vertical. And that is known out of general facts, essentially the theory of Hirsch, Pugh, and Schub that I mentioned. So in all that follows, I'm going to focus on volume-preserving diffeomorphisms. It will be implicit. And then there's a number that we can associate to any perturbation, to any f close to f0, which is called the average center Lyapunov exponent. It's just, you take the derivative along the center. You take the derivative along the center direction. You take the logarithm. The center in this case is one-dimensional, so the derivative is a number, okay? It's one-dimensional. You take the logarithm and then you average that out with respect to the volume measure. And Schub and Wilkinson proved around the year 2000 that there exist diffeomorphisms f close to f0 for which this number is different from 0. If you calculate this number for the original map f0, then the derivative is 1, because remember f0 was the identity along the vertical, and then you get 0. Lambda of f0 is 0. But you can perturb the diffeomorphism in order to make the exponent become different from 0. And their key observation is that then, as a consequence of that, the center foliation fc cannot be absolutely continuous. And this is, as far as I know, the first time that the connection between absolute continuity and Lyapunov exponent was raised. And the argument is subtle. I'm not sure I can explain in 3 lines, but basically it goes like this. If the exponent is positive, what does that mean? It means that the average of the logarithm is positive. So it means that in some sense, on average, the derivative of f along the center is bigger than 1 on average. It's more bigger than 1 than less than 1. And so that means that if you use the mean value theorem, by iterating the center leaves, with the derivative being predominantly bigger than 1, the length of these iterates should grow. And it cannot grow because the length of the center leaves are just circles, smooth circles. They are continuous, a compact family of circles. The length is bounded. So there seems to be a paradox. This condition says that by iterating the derivatives, the center leaves, the iterates, should be growing, but they cannot because the length is bounded. And the way out of this paradox is that, in fact, we are using two different measures. When we speak of average here, it's average with respect to the area, to the volume measure on the ambient manifold. And when we speak of length, it's length along the leaves. And the way nature has to deal with the paradox is to decide that these two measures are unrelated. Volume on the ambient space has nothing to do with the length along the leaves. And that is what lack of absolute continuity means. That's precisely why the foliation cannot be absolutely continuous. It's this disconnect between measuring length along leaves and then integrating that, and on the other hand, just taking the average with respect to volume in the ambient space. Okay, almost immediately, Amie and David Ruel went further and proved that, in fact, a much stranger phenomenon happens if the exponent is non-zero. Then you can find a full volume subset of the torus which intersects every center leaf on a finite set with a fixed number of points. This is perhaps an easier way for me to explain the content of the theorem. This is a picture from Amie's website. It describes a foliation of the torus, of the two-dimensional torus, by smooth circles. These circles are infinity circles, and they foliate the torus. And in this picture, there exists a full area subset which intersects every point, every one of these circles is in 1 point. So there's a way to pick 1 point on each one of these circles, and by taking these points together, what you get is a full area subset of the torus, of the two torus. So you see, area and length have nothing, area on the torus and length along the circles has nothing to do one with the other. You can obtain a full measure, a full area subset by picking just 1 point on each leaf. And we speak of atomic disintegration of area in such examples. So the purpose of my lecture is to further investigate, kind of bring these observations into a broader setting. And we studied different kinds of partially hyperbolic systems. I've written here the keywords, but I'm not going to define what is a fiber diffeomorphism or a center fixed diffeomorphism or a diffeomorphism derived from Anosov, because instead I will just state the results in interesting specific examples of each one of these classes. And what we discovered in this investigation was that at least the first two classes of partially hyperbolic diffeomorphisms, fiber and center fixing, there are two conclusions that were surprising. On the one hand, a very sharp dichotomy of about the behavior of the center foliation. The center foliation either is really good or really bad. Then there's no in-between alternative. And also, the really good case is very strongly rigid. It happens only for very, very specific situations. And then, in fact, the third class of partially hyperbolic diffeomorphism that has been investigated, derived from Anosov, in fact, has a very different kind of behavior, and neither of these two conclusions holds in that case. So, as I said, I will state the results through examples rather than giving you general technical definitions. So the first result is stated precisely for the setting of Shub and Wilkinson. for the map they considered. And it says it's the rigidity statement. It says that if, as we observed, Shub and Wilkinson observed that if the exponent is, the Lyapunov exponent is different from 0, then the foliation cannot be absolutely continuous. This theorem goes further and explains exactly when is it that the foliation is absolutely continuous. And it says that that happens only if, in fact, by starting with F0 and perturbing, you picked a perturbation of a very, very specific type. Namely, you picked another rotation extension. So the only way you can keep the foliation absolutely continuous is by taking F0 and perturbing it into a different rotation extension, possibly different, for some annals of diffeomorphism. And then in that case, this up to a C infinity conjugate means up to a C infinity change of coordinates. So you may think that the perturbation is just another rotation extension. And in fact, in that case, the center foliation is not just absolutely continuous. It's infinity. It's the infinity. So there's no, it is really very specific, the assumption of the center foliation being absolutely continuous, which may seem mild. After all, it's such a mild form of regularity, much milder than C1. In fact, in this setting, it implies that the system is very special, of this type, and that the foliation is very special. It's actually as smooth as you could hope for. So this is the rigidity statement. And then there's a dichotomy, going deeper into this. If one makes an additional assumption that's called accessibility, accessibility just means that given any 2 points, X and Y, you can go from one to the other by following a path, a finite path, which is at each one of these legs is tangent either to the stable subspace or to the unstable subspace. So you can access any point from any point by moving along either the stable leaves or the unstable leaves. And that's a very mild assumption. Just ignore it because it's a very mild assumption. I'm just stating it for the sake of honesty. But with that additional mild assumption, either the foliation is absolutely continuous, and as we have just seen, that implies that in fact it is infinity, or we have atomic disintegration, or we have the kind of phenomenon that that Ruel and Wilkinson discovered, identified, or we have atomic disintegration. So you see, this is a very, very sharp dichotomy. Either the foliation is as smooth as one can dream of, or it is as non-smooth as one can wish it weren't, with this kind of measure-theoretical pathological behavior, where you have a full volume subset of the ambient space, which is formed by a finite number of points on each one of the leaves, the kind of pathological behavior that I described in the picture. So this was this is a statement for this kind of maps, for perturbations of the Shub-Wilkinson maps, and more generally for fibered subspaces. Then there's counterparts for the other construction, center fixing, which includes perturbations of the time-one map of the geodesic flow on a surface with negative curvature. There are statements for higher dimension manifolds, but for surfaces, they become particularly acute. So the theorem is, in this case, the dichotomy theorem is that, similarly to what was said before, either the center foliation is infinity, as regular as you could hope for, or there exists a full volume full volume subset that intersects every center leaf exactly on one orbit. In this context, the leaves are usually the leaves are like open trajectories of the flow, So they are non-compact in this case. They may be non-compact. There are also compact leaves coming from the periodic trajectories of the flow. So in this case, you may construct a full volume measure subset of the ambient space by picking one orbit, one countable set, just one orbit along each center leaf. And there's nothing in between. Either the foliation is infinity, and then it's just the usual familiar setting of Fubini theorem and things like that, or we have a very spectacular atomic disintegration along the center leaves. And perhaps particularly aesthetical, if the center foliation is C infinity, which, as we know, just saw, it's the same thing as being absolutely continuous. It's equivalent to being absolutely continuous. This happens if and only if, in fact, the perturbation F is the time-one map of a C infinity flow. And the trajectories of this flow coincide with the leaves of the center foliation. Let me make a small pause here for us to breathe. You start with the time-one map of a flow, of a hyperbolic flow, of the geodesic flow on a surface with negative curvature, and you perturb it. When you take a diffeomorphism which is close by, we know out of general principles that it has a center foliation. So we are looking at this center foliation and trying to understand how it behaves. And now we have the following picture. This foliation may be atomic in the sense that this kind of phenomenon that I described, or it may be absolutely continuous. And then if it is absolutely continuous, in fact, it is C infinity. And then if it is C infinity, that's because your perturbation, the perturbation that you chose, F, is itself the time-one map of a C infinity flow. And that's extremely rare. Most diffeomorphisms do not embed in flows. They are not time-one maps of flows. But in this case, that's this extremely rare phenomenon is the necessary and sufficient condition for the center foliation to have decent and, in fact, spectacularly good behavior, being C infinity. If you compare with the statement I gave you previously for the other class of systems, you will notice that this time I didn't say anything about accessibility, and that's because accessibility in this case comes for free. In the other situation, it was a mild assumption. Here it is no assumption at all because of the theorem of Grace and Puig-Schuh, where they prove that every diffeomorphism close to the time-one map of the geodesic flow on a surface with negative curvature is, in fact, always accessible. Okay, these statements are based on a statement that was developed over the years by many people, which we call the invariance principle. There are many invariance principles in mathematics. This one is about, I'm going to try to state a version of the invariance principle, but it's called principle precisely because it's not really a theorem, it's a general idea that can be used in many situations. And I will briefly explain what that is, and then I will finish by dealing with the third class of dynamical systems, of a partially hyperbolic dynamical system. So to explain that, let me go back to the Wilkinson setup. I take something, diffeomorphism close to this F0, and these maps, as we saw, have center foliations whose leaves are circles, and we can consider going from one of these center leaves to the other along, say, the stable direction, along this is the stable leaf, along the stable leaf, and by doing that, we can define from one center leaf to another a map which we call the stable holonomy. It's just a projection along stable leaves from one center leaf to the other. There's the dual notion of unstable holonomy, which is defined in the same way, just by using the unstable foliation instead. And what the invariance principle would say in this case is that if the Lyapunov exponent vanishes, which is in principle is the difficult case. I mean, when it's different from zero, we can use general tools. When the exponent vanishes, that's where we were a bit lost on what to do. It's the neutral case, the undecided case. Well, the invariance principle tells us that that implies, if that happens, if the exponent vanishes, then that implies something quite spectacular, which I cannot write in unfortunately in less technical terms, but essentially that the volume measure disintegrates along the circles in such a way that the various conditional probabilities are preserved by this stable, not just by the stable holonomy, but also by the unstable holonomy. And this relation between what happens in different center leaves is this invariance under stable and unstable holonomies is crucial for the proof of those results. Of course, there are many other ideas, but this, I believe, was a central piece. Okay, moving to the last part of the lecture, I want to say a few words about diffeomorphism derived from an Ozov. And that is a study that was pioneered by, from this point of view, of looking at the properties of the foliations. And this was pioneered by Regis Varão. It should be 2015 and 2016. There's a typo there. And what he discovered is that, in fact, the behavior for this class of dynamical systems is quite different. The main difference, and I jump to the final line, the main difference between this and the previous examples is that for this class of systems, the center leaves are truly non-compact. I say truly because in the second case, the center fixing class, there are compact leaves and there are non-compact leaves, a mixture of the two. But we discovered that they could be compactified in a proper way, and that's why those two classes end up having similar behaviors. Here, this is truly non-compact, the behavior along the center leaves. And this is just one sample example of the kind of things that one can prove for this class. If F is a C2 perturbation of a linear automorphism, so again, you start with a 3x3 matrix with integer coefficients and determinant 1. And let's assume that the eigenvalues for this matrix are all distinct in this way. And then what we could prove is that for measures that are sufficiently complicated, and that's what this condition on the entropy means, for measures that are sufficiently complicated, the center Lyapunov exponent is strictly positive. It's non-zero. You don't have to assume that it is non-zero, because it will come up being non-zero. If the invariant measure, this could be any invariant measure which is sufficiently complicated, which has sufficiently large entropy. Then the exponent is positive. In particular, it's different from zero. And in that case, in the two previous classes of dynamical systems, we would expect, if the behavior was analogous, we would expect a kind of atomic disintegration phenomenon, the full measure subsets whose trace on the leaves is actually a finite set, and in some cases just 1 point. And what this theorem says that it doesn't happen. In this case, it never happens, because every full measure subset intersects almost every leaf on an uncountable subset. So this hints, it doesn't prove it, it hints at the possibility that in this case, the disintegration of volume along the leaves is, well, certainly not atomic, definitely not atomic, probably continuous, singular continuous, and eventually possibly even absolutely continuous. So we don't know. The theorem just excludes the case of atomic disintegration and leaves open the possibility that in this case we have the third type of disintegration, not smooth, not atomic, continuous, but singular, and that's possibly what happens, at least in some cases. So you see, the kind of dichotomy that we had before, C infinity on the one hand and atomic on the other, breaks down in this case. And in fact, Regis has other results that suggest that there's no analog of the rigidity results that we saw for the other two. All in all, this is still a class of partially hyperbolic dynamical systems that has to be further investigated. The theory is more incomplete in this case. And then in the recent years, people discovered that against expectations, there are other types of constructions of partially hyperbolic diffeomorphisms, even in three-dimensional manifolds. For a while, there was a statement called the Pujal's conjecture, which I don't think Pujal's ever made, but which was that those three constructions that I described at the beginning are all there is. Turns out that that's not true. There are other examples. So there's a lot more to understand, even still in three dimensions, which is where the simplest possible situation we can consider. And at this point, I stop, and thank you very much, all of you, for your attention.
Yeah, thank you, Marcel, for your wonderful talk. Let me see if there are questions here in the... No questions. Okay, I have some curiosities that, for instance, in both settings, the setting of with Wilkinson and Artur Avila, or even in this setting, could these results be used to understand the problem of continuity of the Lyapunov exponents, say to understand mechanisms for discontinuity, or to
I think so. I think so. As you know, continuity gets tougher to analyze when the exponents vanish. I mean, the behavior near, well, this may be a mysterious statement based on some disappointments I've had. It gets tougher when, in some situations, when not at the point where the exponent is zero, because but at the nearby, and and this describes the structure of such systems. It tells us exactly how they are and the rigidity. And so presumably it could be used, and then you know fairly well how the perturbations are. So presumably this could be used. I confess, I never thought of that from that point of view. So this may be just wishful thinking, but I think so. Yeah. I mean.
Yeah, nice. Well, more specifically in this setting with Amie and Artur, could you get some continuity in the atomic case, not in the other case? Could you hope to get some continuity of the Lyapunov exponents if you know that your diffeomorphism corresponds to the atomic case?
The question, you see, the question becomes, in a sense, I only spoke here for simplicity. I only spoke of the situation where the question is actually quite easy, because I only define center Lyapunov exponent in this formula when the center is one-dimensional.
Yes.
And when it's one-dimensional, there's this formula. So immediately you get continuity, just because EC depends continuously on the dynamics that is known, and of course the derivative depends continuously on the dynamics, and then you integrate, so it's continuous. In this setting, definitely we have continuity. The two-dimensional case, when the center is two-dimensional, would be the obvious first place to look at, and we know. Yeah, I don't know the answer. The honest answer, I don't know. I didn't think about that seriously, but the two-dimensional case is certainly a place where one could and should look at the question. And of course, there's no such formula for the exponents, and we have to resort to Furstenberg's formula or something like that. But yeah, it could be, especially because these things are analyzed in terms of the projective space, which would be one-dimensional. Could be. That's a very good question, Pedro, and the honest answer is I don't know, but I got curious too.
Yeah, thank you, Marcel. Very, very, very nice. Let me see if there are, I guess, no questions. Well, I think this has been the normal thing. People get inhibited of writing questions. It would be easier if they could speak out loud.
Absolutely, yeah,
But
sure.
also, yes. So, Marcelo, once again, thank you very much for this very nice talk, for this beautiful presentation.
Thank you all. It's been a pleasure to be here, and I hope next time we'll be in person, and after the talk we go out for a cup of coffee.
Yeah, yeah. Let's hope soon we can do this.
Okay. Bye-bye, everyone.
Okay. Bye-bye. Thank you.